We're going to continue our discussion of virtual memory systems. It's funny because I mentioned virtual memory all the way along. In fact, that was one of the things that I mentioned. If you want to do well in 124, make sure you understand virtual memory before you start the course. And so we haven't really talked about it formally all the way until last lecture. And we have this kind of a picture where programs always use logical addresses. Those go to the processor. The processor emits to the rest of the hardware physical addresses. And the address translation is taken care of by this component called the memory management unit. So that's basically all the stuff here. Probably the most interesting part of last lecture was the fact that there's been a whole bunch of different ways that this has been done through history. Like in 24, we talk about page tables, and page table hierarchies because flat page tables tend to take too much space. They have a sort of a fixed requirement on how much memory is necessary for the translation, and by changing it into a hierarchical paging mechanism, we can make it scale with the virtual address space size of the process. So if it has a lot of junk, the page table is big, and if it has just a little bit of junk, then the page table actually turns out to be quite small. So that's the current modern way of doing it, but it hasn't always been this way. And I also mentioned, as an aside, for the people who weren't here and haven't listened to the previous lecture, probably won't remain that way, because even hierarchical page tables have this issue that as the page table depth grows, then I'm incurring this cost every time I descend down the hierarchy. And you can design clever caches that handle partial hits and junk like that, but the cache gets more and more complicated, and then it gets slower, and then address translation slows down. So whether this will continue to be the way we do things in 10 years, 20 years is an interesting question. I don't know the answer to it. If I did, I'd probably be incredibly wealthy. So, and I'm not. So anyway, so these paging mechanisms map virtual addresses to physical addresses, which give us all kinds of powerful capabilities. We talked about that as well, blah, blah, blah. We talked about the benefits of this as well, and the two obvious one is address space isolation. That's really important, and then also having a simplified ABI or application binary interface so that it's easy to write a compiler, it's easy to write a linker, and just have all the processes follow the same address layout. Okay. Now, the other benefit, which is going to become valuable really quickly in your assignment, is the fact that we can now move page contents back and forth with a backing store, swap storage. All these terms are kind of equivalent. And so that allows us to overcommit physical memory. I have 1 gig, I want to run 10 gigs worth of programs all at the same time. No biggie, because most of the time, programs don't always access all of their physical memory. In fact, if they do, that tends to be considered bad behavior. So that's one of the interesting things about program behavior is that since they don't, their working sets tend to be much smaller than their full actual virtual address space, we can do this, and it works really well. And another aspect of this is if I don't use a program at all for a while, well, the OS can just swap it out. I mean, there'll be times, I have to write things just like you guys do, and I don't like to do it, just like you guys don't. And so I'll leave Word open, and it'll be open for 2 weeks, and none of the pages will be loaded, because I haven't touched it, I haven't run it, and so the OS has swapped it all out. And that kind of thing becomes really a powerful capability. Okay, so to be able to support this capability, we need to have page tables with some useful information. And so this is probably going to be somewhat review oriented compared to the way CS24. We cover a lot of this stuff in CS24. But one of the things that we need to do for the page tables is have some way of recording whether or not a particular entry corresponds to a virtual page in a physical frame or not, so that we can have the OS and the processor interact with each other in clever ways. So valid-invalid bit is the obvious extension, so that we can say this entry is in use or this entry is not in use. And like here, valid or invalid or present and not present. I like IA32's present bit. I think that makes a lot more sense. Basically saying, yes, there is a page present in this frame. Remembering the terms, a frame is a physical page, actual region of physical memory. A page is typically that term means a virtual page. So it's a chunk of memory in a process's virtual address space. Okay? And of course, if the valid bit or present bit is 0, then the MMU is going to ignore everything in the page table entry. Now, that gives us an interesting opportunity. You can see that when the valid bit is 1, that the MMU assumes that the rest of the entry means something specific to the MMU. What's the physical page number? It's used for address translation. Anybody who reads the IA32 x86 manuals, it's got all kinds of junk in there. It has all these bits that mean various things. Okay? So the MMU is expecting all those things to mean something, but if it's 0, the OS can use that entry for whatever it wants. Okay? Most OSs use that for something specific. Okay, so the MMU does a translation, and it examines the valid or invalid bit first, and obviously if it's valid, the MMU does the translation. It assumes that everything is under control. Okay? If the bit is invalid, then we get a fault. Okay? And the interesting thing about this is that not all page faults are the same, and this is one of the things that I think a lot of people get confused by at first, but it makes total sense. Sometimes I generate a fault because I dereference null, or I try to write to read-only memory, or something like that. Clearly a bug in my program. And in those cases, the OS would terminate the program. Other times, I get a fault because that page is just not in virtual memory, or I should say it's not in a physical frame. So then the OS needs to resolve that. So you can see that the OS has to make this distinction or determination of whether or not it can resolve the fault. Okay? This was our little example from CS24. So we have 4 frames, 8 virtual pages. It's funny because I mentioned the PDP-11 last time, where the PDP-11 has just 8 registers that specify the memory mapping. This is at a PDP-11 level of sophistication. So we have a simple page table, and some of the virtual pages are in physical page frames. So you can see they're labeled PF0 through PF3, that's page frames, and what virtual pages are in there. Okay. Some virtual pages are on the backing store. In this case, you can see that a few of them are specifically only there. And then 2 of the pages have not been allocated. So 0 and 5 have not been allocated. Now, the first thing that I would mention about this is that it's kind of up to the OS to decide how to distinguish between some of these cases. If it's in physical memory, well, we have to follow the MMU's spec. But if it's in a backing store versus not allocated, that's up to the OS to determine how to represent that, and obviously how to organize the backing store and how to deal with a few other details. That's all specific to the OS, because the MMU is like, I can't deal with that, so it's going to be up to somebody else. Okay, program access is a word in virtual page 2. So again, the MMU gets the virtual address, and it looks up in the page table to do the address translation. It sees a valid bit of 1, so it's happy. It does the address translation, sends out the physical address to memory. Everything goes fine. Okay. No faults. This is great. Okay. Next, we get an access in virtual page 6. And again, we're all smart, clever human beings, so we look in the page table, see PTE6. Valid bit is 0. Okay. So the MMU knows it can't deal with this. And again, its level of analysis doesn't go any further. It just says fault. And so it tells the kernel, this is your problem. And now it's up to the kernel to determine, well, what kind of fault is this? Can I resolve it? Can I not resolve it? And so in this case, let's just say by looking at the rest of the entry in the page table, it says, oh yeah, that's in the backing store. I know where it is. And so I can move it back into memory. But of course, we have an issue here that no frame is available. Okay? So this is the other part of the thing. A lot of times when we have a page fault and we have to page something in, well, if we have a system that is under any level of use, and you'll probably encounter this in Pintos, page in means that we have to page out first. And so we have to evict. Something decides which victim page. Remember, that is a policy decision, so that's going to be something that is typically modularized so that we can swap in and out various policies. The mechanism would be what are the steps we have to implement to page out a particular page. Okay? So we do want to avoid writing to the disk if the virtual page's contents didn't change, so we'll talk about that problem more in a second. So that might be skipped, but otherwise we might assume that we may need to write it out. Okay, so like I say here, we may have a dirty bit that says, yeah, this page was written, so that we know if we need to evict it. Okay, so let's say that that is the page that was evicted, blah, blah, blah. And so now we can update that entry in the page table to say this virtual page is now in the backing store. It's not in a frame anymore. And then we can go ahead and load virtual page 6 into memory. Okay, update the page table. Now the neat thing about this is the kernel now returns from the fault handler. Okay. And so because it's a fault, the CPU goes back and reruns that specific instruction. And all of the machinery runs again. Okay, and this is the thing that's funny about this to me is that it's not like the processor knows that it's returning from a page fault. I mean, at some level the processor has to know so it can go back to the same instruction again. But it could run the same instruction and fault again if you have a bug in your OS. So there's a lot of fun ways you can completely screw things up. And it is conceivable that you could have a fault instruction that never gets resolved and you just sit in an infinite loop bouncing back and forth between your fault handler and the instruction. Okay? You may see that behavior. I hope not. But anyway, the program repeats the access to virtual page 6. The MMU comes in and looks at the page table. This time, valid bit is 1. So it does the address translation, and everything goes on perfectly fine. Okay, that's the process. We talked about the concept last class, CS24, but now we're talking about how to implement this stuff, because this is what you're going to have to build. Okay? So any general questions about this? One thing you'll notice is we sort of talk about this like, oh, a program faults, and then this page gets evicted, and then that page gets loaded, and then we go back to the instruction and run it again. How many context switches have occurred in this process? You might say at least one, because we know we are doing at least one I/O operation, and so we're going to be blocked on disk for a while. But it's quite conceivable that we may have many context switches, because we're talking millions of instructions, typically, for doing 1 or 2 disk IOs, writing stuff to disk, reading back the other thing from disk, and so forth. So this is one of the details about page faults. Page faults are great opportunities for context switches. And that generally is how things work in the OS. That's the way your page fault handler will work. And you'll probably have some code that says, I want to go do some disk IOs. And when you do, that's going to yield the processor to some other kernel thread, and that'll resume running some other process. So you can see that you have a number of interesting issues that can fall out of this. One is that you need to do this in a manner that is safe from a multi-threaded perspective, because you're going to stop doing stuff and other threads are going to start doing stuff while this process takes the time that it needs to take. This also, by the way, remember that sometimes memory allocations generate page faults, because I may need to extend the size of my heap, and somebody might go and access part of the heap that hasn't been allocated to the process yet, so that generates a fault. And so this is why we have to be careful about memory allocations within kernel threads running in interrupt context, because page faults are slow and may involve blocking the current process or current thread while we resolve the fault. Okay? So there's a number of interesting details about this that you don't really think about until you get into the implementation. Okay, dirty flags. Dirty flags can be tricky as well. Primarily because of this issue of aliasing. You can have 2 virtual addresses that refer to the same page frame. And when they do, then you need to think about what page table entries actually get updated. Remember that we have a dirty bit, sometimes we have an access bit, which helps us make paging decisions. But the MMU only knows about the page table entries that it has to use for address translation. So if we have a situation where multiple page table entries refer to the same frame, then we may have some entries that are modified in some ways and others that are not. Okay? So if, like I have here, if you have multiple virtual pages, mapped to one frame because you're sharing, either you have shared read-write memory between processes, very common way of doing inter-process communication. Shared libraries are an obvious example of this. The one that you'll run into in Pintos in Project 5 is pages in the kernel's page table. Actually, I think you run into this in Project 4 as well, but Project 5 it actually becomes serious. So you have pages that are mapped into the kernel page, how should I say this, kernel space as well as user space, so you have to think about that. Okay. So when you have an access, like I was saying, you're only going to have one page table in effect at any given time per processor, because each processor has its own MMU, and that will set the bits of the page table entry through which the access was performed. Okay, so in this case, we have page frame 1 is mapped by two different processes' page tables. For process 1, it's page table entry 5, and the other one is page table entry 1. Okay, so they both say that they're available, or I should say they're in memory. But if you have a write to one of these entries, then it's only going to set the one entry's dirty bit. It's not going to set the other one. Okay? So here we have a situation: process 1 writes to virtual page 5. Dirty bit gets set to 1. Later, so stuff happens. Process 2 is running, or maybe process 2 is not running, but somebody decides it's time to evict one of these frames. And so it says, I want to evict virtual page 1 from process 2 out of the physical page frame so that I can now use that for something else. The only issue is that that page table entry doesn't record that the page is dirty. And so if you look solely at process 2's page table, you might not know that you need to write that page back to the backing store. You might not, or the disk file from which it's taken, or whatever. Okay? So this is no bueno. So the kernel has to think about these kinds of things. That's one primary issue that you have. Now, I don't think any of us have really, well, certainly none of us have talked about the frame table or anything like that. But when you read Project 5, you'll start to see this kind of stuff. This is part of the reason why we need a frame table, so that we can know who all is using a particular page frame and for what. Okay? You need to be able to handle this. Now, I'll just mention as an aside that shared memory is an extra credit item for Project 5. If you blow the rest of Project 5 out of the water and you're like, now I want a real challenge, try implementing shared memory. It's totally doable, and this is an example of the kind of thing you have to think about. Okay? I think it's probably a straightforward extension of the rest of Project 5's capabilities, as long as you've done things in a careful way, you've avoided bugs along the way, and your design can facilitate it easily. Okay? So here's the deal. When I'm going to evict a page out of a frame, then I basically need to look at all the processes that might be using that frame. And the reason why is because I need to look at all the page table entries. Do any of them have this marked dirty? If any of them have it marked dirty, then I need to write this page back to the backing store, back to its file from which it's from, before I can go ahead and reclaim that frame. Okay, so that's important. That may seem wasteful, but it actually turns out that you need to do this anyway. And this is one of the things that I think is kind of neat, because if you're going to implement a shared memory abstraction, well, if you have a frame that's in use by a bunch of processes, guess what? When you move that page out of the frame, you need to modify all the processes' page tables, because all the processes need to know that that page is no longer present. So you can see that you have to do this anyway. So again, the frame table will say, hey, process 1 is using this frame for virtual page blah blah, and process 2 is using this frame for virtual page blah blah. Okay? So you're going to have to store that information anyway, so that you can go through and modify those page table entries to say, this page is no longer in memory, now look on the backing store. Look somewhere else. Okay? So There are various ways to make this cleverly fast, and you'll notice that a lot of OSs come up with very clever ways of doing this. Let me see what else I say on this slide, because I don't actually talk about this very much in this lecture. Okay, I think I talk about it a little bit more in a future lecture. But one of the things about, for example, IA32, so we're working with IA32. Remember, we have 32-bit page table entries. The bottom bit is the valid bit or the present bit, so you have 31 bits to do whatever else you want in there. Now, since 32-bit architectures have 32-bit pointers, and since most of the time when we allocate things, they're word aligned, well, that means the bottom bits are usually going to be 0. Like the bottom 3 bits will be 0 if you're aligning on 8-byte boundaries. Or if you're aligning on 4-byte boundaries, then at least the bottom 2 bits will be 0. Which means that you can store a pointer in the rest of the page table entry and use that to point to some data structure. And this is what Linux does. It actually chains together the information for a particular page table entry so that it can go look things up. And the same with the frame table. The frame table is a very compact representation of what processes are using a particular page frame. And so it's able to chain processes together so that traversing the processes that may be sharing a page becomes pretty easy. Okay? So there's some very clever hacks that these systems use to make everything efficient and fast. Now, that said, you guys are lucky because we're doing Pintos, and Pintos can be slow and crappy, and nobody cares. Like I said, the neat thing about this OS is that you get to throw your project in the bin in 2 weeks when it sucks. So you're like, that was terrible. I don't want to do that. You don't want to build the file system on top of virtual memory. That's totally fine. You don't have to. So the nice thing about Pintos is you don't have to actually leverage the page table entries to store information when a page is out of memory. Okay. In fact, the assignment actually recommends that you don't. So, but if you want to, you certainly can. It turns out that you can build a perfectly capable virtual memory system without doing that. And that's actually what the solution implementation does. It doesn't even use the page table entries beyond setting present bits and so forth. Okay, swapping and paging. So this facility means now I can move parts of processes out of memory. And the only reason I bring this up is remember that the alternative we discussed last time was standard swapping, where we suck the whole process out of memory to the backing store, and that could be really slow. Like historically, it's always been slow, and even on our modern systems, it would be really slow to move a multi-gig process to the backing store. It's like nobody wants to do that. Okay, so the other thing that's really cool about this is that we can actually build a system that only assigns pages when processes need them. Okay, so we call that demand paging. How do you demand a page? By faulting. And then the OS kernel has to step in and handle the situation. So we only swap in a page or we allocate a page to a process when the process needs it, and we know that it needs it because it generates a fault. Okay. Now ideally, now it's in memory and we access it and everything is hunky-dory until some other process needs a page and then that faults. And so we don't want to let faults grow out of control. But in general, we only put stuff in memory when somebody needs it. Ideally, this gives an optimal memory utilization. Okay, so we optimally utilize our physical memory. And we'll talk about that in the future as well, because there's some really unusual things about paging policies that you can run into. Okay, running a program stored on disk. This is the idea. I set up a page table. I reference the program's binary. Okay. But you'll notice here that none of the pages are actually in virtual memory. So you could go through the page table structure, and every page table entry would say valid 0, valid 0, valid 0. So we haven't actually consumed any physical frames for running this program until it starts to run. And obviously the first address we access, 804.8000, tends to be where that is on 32-bit Linux. Somebody tries to access it, causes a fault. The virtual memory system brings that page contents out of the binary and into physical memory somewhere. Okay, maybe that needs to evict another page, we don't know, But anyway, the first thing gets loaded. As long as we're in that first page, we just keep running, and that's cool. Okay? But then when we leave the first page of the binary, then we get another fault that loads the second page of the binary, and so forth. Okay? So this is the idea behind demand paging, and hopefully everybody here can see that this would sort of minimally use our page frames. We only allocate them to a process when we need to. Now, how do you feel about this from a performance perspective? I want you to think about this, because most OSs don't actually do demand paging. And there's a really obvious performance-related reason why. Yeah?
It would be faster to, like, if you know that like there's 5 pages of the binary that you need to load, is it faster to load it all in one go?
Yeah, that's exactly right. 5 pages or even 1 page, ideally, because we're presuming that our program has loops and things like that. But we know that our program is going to need a stack, almost certainly, right? If we know that it's about to start running, we know it's going to load the first page. So, and if we're getting toward the end of the first page and we're context switching in back into the process and we notice that we're like toward the end of a page, why not load the next page? So that's prefetching. And you can see that that doesn't minimally consume page frames, but it allows us to get some of the IOs out of the way before we actually need that memory to be in physical frames. And so demand paging, or pure demand paging, especially where you only do this, maybe has minimal memory requirements, but it's just not as fast. And I've mentioned this over and over again in my classes, that usually it's easier to come up with more space than it is to come up with more time. And so, in general, if we can sacrifice some space to save time, we do. That tends to be the way things work. Yes?
So how is it faster to... Because you're still loading the page, right? So you still have to do the IO, so how is it faster?
So the I/O is happening in the background, like through a DMA transfer, if you're talking about any real, like, modern OS with good device drivers. And so the processor can basically be completely uninvolved in that transfer of information. And so it can be running instructions from, let's presume the process that's going to be needing that data soon but doesn't need it yet. It's basically the kernel is preemptively initiating the load on behalf of the process. And the process, of course, as long as it's only interacting with memory, maybe it's even sitting behind processor caches and doesn't need to touch main memory at all, then it should be able to progress for a while so that you actually can overlap the disk I/O of the next page load. So that's the idea. You'll see a better example of this in Project 6, to be completely honest, because a lot of times where the kernel does a big improvement is by doing I/O prefetches based on program behavior. So I'm scanning through a file, like many programs do. I'm scanning through a file, and the OS kernel says, oh, well, I'm going to just preload, I'm going to queue up a bunch of loads. And that's where you get the benefit that you mentioned earlier. Like if I know I need 5 disk blocks, well, in all likelihood, those are all going to be in the same cylinder on the drive, presuming spinning disks. I suppose happens from time to time these days. And so in that case, you'll get a huge performance benefit of loading all of those things in the same cylinder at once. So, but there are situations, especially when we're paging in a program, where it makes a lot of sense to say, well, these are the pages that have been used most recently for that process. So let's just make sure they're all paged in. So you get benefits there. So, okay, lots of fun stuff to discuss there, but I don't want to get too distracted, even though I think we'll easily finish this lecture on time. Okay, so that's demand paging, and that's just an idea. I don't mind if you guys do demand paging for this lab, but or Project 5, but you may find the assignment write-up suggests that you may want to pre-allocate the first stack page for processes in Project 5. You may want to, well, actually, you know what? I think the assignment guidance is that the entire binary should be demand paged. There's no way of exercising that, so I'll leave it up to you. I mean, the point of CS124 is to get out alive, not to have like the most amazing OS ever. So if you want to try to preload the first page of the program, be my guest. But if you decide to purely demand page it, that'd probably be the simplest thing to do by far. So, Okay, demand paging. So yeah, managing a process memory heap. This is really common. So the kernel will say, yeah, I'm going to allocate this virtual address range for your heap. That's totally cool. But it doesn't actually assign any frames to that memory because why? Why would it do that? Okay? If you never call malloc, and there are plenty of programs that never call malloc, I write quite a few that never call malloc, then you don't need to actually allocate any frames to that region of memory. So the process interacts with the heap. Well, then the kernel will go ahead and allocate pages into that heap to back the memory. Okay? So that's cool. But let's say that over time your allocation region grows. Well, then at that point the kernel gets involved. Okay? And that's there are a couple of APIs used for doing this. There's sbreak. You'll see that mentioned in some documentation. That's old Unix API call. More recently, I think it's like setar limit, something like that, is used for setting the resource limit of the memory heap. And that's a system call because it involves manipulating the process's virtual memory area. Okay. So, yeah, the kernel will basically take care of that. No big surprise there. Now, you do eventually run into the situation where there's no more frames, and that's a sad day. Not really, I mean, because the kernel has a way of dealing with that. Basically, then it needs to figure out what page can be evicted from what frame so that we can free that frame up for something else. And so that's where the page replacement policy comes into the picture. We're going to spend a couple of lectures talking about page replacement policies because they're kind of fun. Again, you don't have to implement a complex one for your Pintos implementation. Like, I think it's clock. I think they suggest like clock or second chance is perfectly sufficient for the assignment. But anyway, you take the page, write it to somewhere on disk, okay, and then the frame is available to use for another virtual page. Okay. So then you have pure demand paging. This is just to introduce you to the term. Remember, demand paging is I give you pages or I give you frames as you actually require them, as you access them. Pure demand paging means you only ever do it that way. Okay, so technically, when you do your Pintos project, if you assign an initial stack page, then that won't be pure demand paging because you would only do that when the stack is actually accessed for the first time and you get a fault. Okay, and we talked already a lot about how kernels generally don't do pure demand paging because it's too slow. We want to try to overlap I/O with CPU-intensive operations as much as possible, and so typically you'll see a lot of prefetching going on.
Oh. So when you have things like the heap, it seems to suggest that you want pure demand paging for the heap because you don't want the prefetching.
Yeah.
Does that mean pages have some idea of the content they hold then?
It's a good question. I think in general the OS kernel is more familiar with what pages hold, and the pages themselves are kind of simplistic. I mean, it tends to be that they're just represented by simple data structures that say, this is where I'm from initially, and this is where I go when I'm kicked out. So it tends to be that that's what virtual pages tend to have. But for example, when the OS kernel is setting up the memory map, and you guys will do this, like this is one of the things you'll have to do for Project 5 is go change process.c and put in like what to do when you see different parts of the process address space. The kernel very easily could say, I'm going to map in .data, .ro data, so I'm going to set that apart, set BSS up so that this is all the data segments for your program. And now I am also going to give you like 2 megabytes of pre-allocated page frames so that you have a space for a memory heap. And then it'll say, if you want more, well, cause a fault, and then I'll find out. Okay. Same thing with stack. A modern operating system might say when it's laying out the stack, I'm going to give you 4 pages of stack right off the bat because I expect you're going to need it. But then if you need more than that, then you're going to have to fault. So it kind of is up to the OS to make guesses about how it wants to resolve these kinds of situations. Okay. So yeah, it's kind of an interesting thing. The OS kernel can be really clever. Sometimes they're clever. They're too clever for their own good. And I think that's one of the secrets of 124 is to not be too clever for your own good because the requirements aren't super high, thankfully. Okay. Any other questions? Sweet. All right, copy on write. So again, we're all familiar with this notion of copy on write because we talk about it in CS24. But the idea is when I have two identical copies of something, don't actually make two copies because that's going to use a lot of frames up. Instead, what I can do is make the copies share one set of frames and make them read-only so that when somebody tries to write to it, I can pretend I can actually do the duplication at that point. Okay? So forking processes was a really common example of that. As the parent and child write to various parts of their address space, you get faults because you have a write, and then that page will be duplicated, and so the state starts to separate out to maintain process isolation as the programs execute. Okay. So that's copy on write, really. Important detail, while pages are shared, they can't be written to, so they'll be marked as read-only. They'll generate a fault, and then it's up to the kernel to resolve that fault. Okay? Now here's something I want you to notice about this. What's all the information in the page tables? And we've talked about what goes into a page table entry at this point, and it's like some address junk, and then there's a present bit or a valid bit, and we have a dirty bit. Maybe if we're lucky, we have an access bit. We're all lucky. We get an access bit on x86. But we don't have junk like copy on write. We don't have stuff like what file is this mapped from. We don't have that information in the page table. So already that should indicate that we need to have extra information. As an OS implementer, you need to keep extra information about the virtual memory map to be able to implement these kinds of clever features. Okay, so I'm going to talk about that more in a second, I think, but we'll just finish copy on write. We try to write to a read-only page. We get a fault. The kernel determines, again, not from the page table, because there's not enough space in there to figure this out, but it figures out this is copy on write area. So what it can do basically is say, is this the only process with this page? If so, then I'll just change it to be read-write. Off we go. Otherwise, if there's still processes sharing the page, then it will make a private copy for the writing process, and then it can go ahead and perform the write to its local copy. Okay. So that's all pretty clever. This actually became really important when the Unix process API became widely used because initially fork didn't use a copy on write mechanism. And so when it would fork, it would actually literally duplicate all the pages. And we're talking slow computers. Yes, the programs were small, but memory was really slow. I mean, we're talking like half a second for interacting with memory. It's really great. Like some of you have seen the panels that I have in my office from magnetic core memories, and they would have like a brick of those things. You can still buy them on eBay. I really want to buy one and put a USB port on it. I think it would be so cool. But that brick would only hold about like 16 kilobytes, and I don't know that I could store anything useful on it. But you would have these different planes, and the planes would be interacted with in parallel so that you could actually get enough performance to interact with this memory core. So you can imagine how a computer like that would perform when you fork and copy a process and you copy everything in it. Okay? So it was horribly slow. And this whole copy on write abstraction made things a lot faster. And so that's where the Unix process abstraction started to become useful and effective. Okay? Nowadays, we kind of take it for granted. Now, I did want to mention one thing. You guys have built a command shell. And so you've done the whole fork exec thing. There's an interesting API call that you can utilize when you're building command shells if you want them to be more efficient. We have this common case. I fork, and then I do a little bit, and then I exec. Okay? Well, the reality is if that's my use case, then why would I even set up a copy on write thing? Why would I even want to do that? Okay? So there's a special API call known as vfork, which basically doesn't duplicate the parent's page table. It doesn't set up private copy on write. vfork means the parent and the child have the same address space, which is really scary. Okay? They actually point to the same page table. The presumption is that when you do this, you're expecting the child will immediately go and reinitialize itself into a different process. Okay? You can imagine that if you had this kind of situation, it would be very easy for the child to just shoot its parent process in the head. Okay? So vfork is an interesting one. If you ever have a situation where you're forking and then immediately want to do something where you're completely changing the process address space, use vfork instead, and it'll shave some time off of your implementation. Okay? Thankfully, you don't need that for your command shell, but I suppose if you were writing a real command shell, you'd probably want to do something clever like that. Okay? Oh, yes?
Relating this to the current assignment, so exec.ve would then call the sysexec that you write?
Yeah. Yeah. So exec.ve, yeah, that has to drop into the kernel. Because think about what it's doing. It's manipulating the virtual memory map of that process. And that is definitely something that the kernel does not want user processes to do. So exec.ve will basically make sure the binary exists, check permissions, blah, blah, blah. You guys have already seen that from the user space side of things. And then it'll open up that binary, like presuming it's the ELF format, and it'll go through specific ELF sections, .init, .text. I don't remember all of them, but .init, .text, .data, .rodata, .bss are the obvious ones. Okay, and it'll set up the virtual memory map based on what those sections say, and it'll configure all of that, and then it'll reinitialize the machine context to point to the start of the process, and then that process will go back into the ready queue. And the next time we restore that process's context, it's going to end up at the beginning of the new program. Okay, so that's basically the way exec works, and all of that has to be done in the kernel. Like basically, none of that is is a process allowed to do by itself. So, yeah. Okay, any other questions? Alrighty, so let's see what else I have to say. Yeah, so this is kind of the thing that I was driving at earlier or alluding to. Is that all of these facilities that we can implement with a virtual memory system require much more information than the processor's MMU page table structure can possibly encode. And so almost always we have supplemental information. The assignment calls it a supplemental page table, and that's probably a good description of it. Linux calls it a memory map. Like, what's the virtual memory map of a process? And I think that's also a really good term. But basically, to give you a little idea of how this all hangs together, you have these memory area descriptors, and they're chained together. And you can see that each one says, I apply to this address range, so VM start, VM end, describes details that are not in the MMU page table. And then it links to the next region. Okay. Now, these can be totally clever. And this is something that you'll have to do for your assignment. You'll have to have some equivalent to VM area structs describing the Pintos equivalent so that you can implement the Pintos virtual memory abstractions. Okay. Now, Linux does this on a region level so that it doesn't need many of them because most of the time we have contiguous regions. You guys can do it on a per page level if you want. You can do it on a per region level, whatever you decide you want to do. I probably would encourage a page level. Just simple, right? We don't care about wasting memory because we're an instructional OS. Yes?
Hey, Doug, what's a task struct?
Task struct is basically the thing in the Linux kernel that corresponds to a single process thread.
Okay.
Yeah. Yeah. So that would be like your, what is it called? Thread T? Is that what it is? I can't remember what it's called in Pintos. Yeah, it's a struct thread. Okay, so it's not, they didn't put an underscore T on the end. But I think one of the things in that thread struct is a page table. Okay, and so you can add, and that'll be the whole thing that's set on control register 3. You can add supplemental information to all of this very easily. Okay, so let me see. I don't want to get sidetracked. This stuff is fun to talk about, but we have a limited amount of time now. So yeah, this is from Linux 2.6. Yeah, so let me just throw that all up there. I think I've already described a lot of this pretty well. So mmap is the supplemental table. PGD is the actual thing the MMU uses. Okay, the page directory pointer. Okay, and so that describes all these things. Important detail here, normal memory accesses, supplemental page table is not touched because the MMU is able to handle everything by itself. Okay, so we like that. It's fast. We don't want to touch our data structures if we don't have to. Okay. Now, when you have a fault, then the kernel has to decide, is it an okay fault? Is it a bad fault? If it's an okay fault, how do I resolve it? You know, all of those kinds of questions. And so this is where the VM area structs become essential. Okay. So imagine you've got your page fault handler. One of the things you get to know inside the page fault handler is what was the address that caused the fault. Okay. Well, then you can go and look through your supplemental page table and say, okay, what does this address correspond to? Okay. So you look to see if it falls between some VM start and VM end. And if it doesn't, you already know this isn't in the address space. The process shouldn't be able to access it. So SIGSEG-V, that's what Linux does. You guys won't do that. You'll just kill the process. If it does fall within some VM area struct, then you now have information about, you know, where that thing should come from, like what is going on. Okay, so like I said, if it's either swapped out to storage or it hasn't been allocated by the kernel. So in this case, notice I'm saying an access to a data region of memory. Then basically the kernel can go ahead and load it from the appropriate location. Okay, or if it's not allocated, it can just zero fill a frame and put that into the process's address space. Okay, we're going to talk about this in a lot more detail in the future. But you can see generally how this all hangs together. Okay. Now, if we get a protection fault, for example, because the process tried to write to something that's read-only, tends to be what we would see. I suppose you could even see where the process tries to write to kernel space. There will be tests that do that. They're already in Project 4, so I would expect that. But again, the kernel can look at the corresponding VM area struct and say, is this copy on write, or is it .text, and you should never be able to write to it. Okay, so the kernel can again take care of misbehavior quite easily in that fault handler. Okay, but if it is something that the kernel can support, then the kernel goes ahead and does the necessary thing. So, for example, duplicating the faulting page and then updating the process's page table to point to the new thing. Okay, so are there any questions about the high-level details of this stuff? So let me tell you a couple of things just to make you happier, because I like happy students. I don't believe you have to do copy on write. You have to do kind of a form of it, and I'll tell you a lot more about that on Friday's lecture when we talk about Pintos. But if you think about it, pages can either come from a file, or they can come from nowhere, like zero fill. We call it the anonymous file. When you swap it out, it can either go back to the file, or it can go to the backing store, the swap space. Okay. And so the interesting thing is you may have something that comes from a file and goes back to the file, or you may have something that comes from a file and then goes to swap. Depends on whether or not those changes are supposed to be public. Okay, so that's one of the things that we'll need to talk about in the future. So you'll have to do something kind of like copy on write, but it won't really be that difficult. The other thing that should make you super happy is that Pintos has no user space malloc. Because it has no user space malloc, you don't have to worry about a dynamically resizable heap. Because you don't have a dynamically resizable heap, that means that a big chunk of work that real OSs have to do is off your plate. So that's pretty cool. Yes?
Basically, because like you don't have to worry about, if you resize the heap, you'd have to restructure the VM area structs.
Yes, you would, but the other thing I think that's a little bit more difficult is you'd have to have a special system call for changing the breakpoint. Breakpoint is a terrible term. The system break of where a process's heap ends. So there'd need to be another system call for it. And I think the people who created Pintos said, just not important enough for us to provide that level of functionality, especially because if you have a program that needs a lot of memory, well, then it can just declare a giant array, and that'll appear in its .bss, and then at process load time, the virtual memory layout will be set up to include that space, and then the program can just use it. So I think they didn't really see fit to create a user space allocation facility. So that'll be it. Okay, last slide. We will pick this up next time. So see you on Wednesday.